This is the second unit dealing with soils. We have seen that soil is a naturally occurring thin layer over the Earth's crust that exists as an unconsolidated porous medium composed of minerals and organic matter formed by weathering and decomposition processes that is biologically active and varies spatially across the landscape. Here we are particularly interested in that aspect of soil that is an unconsolidated porous medium composed of minerals and organic matter. That is, we're interested in the physical properties of soil. Recall that the function of soil in the context of plant growth and development is to provide support for the plant to be the source of mineral nutrients that are dissolved in the soil water or soil solution and that are available to the plant, and that can permit the function of roots in the presence of atmospheric gases like oxygen and carbon dioxide. The function of soil is influenced by its physical properties. Physical characteristics of soil include texture, particle size distribution, structure, organization of the particles, and bulk density and volume. Texture and structure affect air porosity and water retention. The physical properties of soil are of particular importance in constructed landscapes, where trees, shrubs, and herbaceous plants are grown. Oftentimes, physical characteristics, such as drainage and aeration, are the most critical ones for long-term performance of such plants. So an understanding of these properties of soil cannot be overemphasized. This unit is divided into two parts. The first deal with soil texture, and the second with structure and bulk density. Soils containing only about 1 to 6% decomposed organic matter are called inorganic or mineral soils. Soils with higher organic matter content are called organic soils. Mineral component of soils are primarily sand, silt, and clay. Other components include gravel and larger rocks, but these tend to be much less significant from the standpoint of the soil's function as a medium for plant growth. As seen in the unit on soil formation processes, these soil mineral particles are derived from the decomposition of rock slowly over time by the action of a variety of physical, chemical, and biological weathering agents. Because parent material and factors affecting soil genesis are unique to each location, mineral particle sizes, the relative proportion of larger versus smaller particles, and the amount of organic matter in a given soil can vary tremendously. This variability has given rise to more than 22,000 types of soil that have been classified by the USDA, that is the United States Department of Agriculture. An example of this variation in soil can be seen in this map of the continental United States that illustrates the distribution of organic matter across much of the country. Large areas of soil high in organic matter, depicted as nearly black areas here, are found in the upper Midwest, where tallgrass prairie used to be a predominant ecosystem. Areas with soil low in organic matter, shown by the gray color over here, are found in the desert Southwest. Similar variation in other soil features is common across the country. Ohio has a wide variation in soils, where there are large areas of the state with generally similar types of soil, but still over 450 unique types of soil have been described for this state alone. Probably the single most important and nearly permanent feature of a soil is texture. Many physical, chemical, and biological characteristics of soil are related to texture, making textural determination one of the most basic of soil analysis. This texture has profound effects on other physical properties of soil. It is essential to understand that the relative abundance or the proportion of sand, silt, and clay in a given volume determines the texture of a mineral soil and also its ability to hold water. For convenience, mineral particles are classified as gravel, sand, silt, or clay according to their relative diameters. Particles larger than 2 millimeters in diameter, the gravel and stone mentioned before, are considered coarse fragments and are not included in soil texture classifications, although these larger fragments can be important in specific localities. One way to visualize the particle size distribution is to think of a grain of sand as the size of a large beach ball, silt as the size of a frisbee, and a largish clay particle as the size of a dime. You can get an idea of soil texture from its feel when rubbed between fingers and thumb. Textural determination by the feel method is important to soil scientists and others working in soil survey, soil conservation, and land use planning. The ability to identify soil textural classes by feel allows scientists to approximate and delineate soil properties in the field. Practice is the key to success in determining soil texture by feel. Another way to examine soil texture is to mix soil and water and observe the layers that form when different sized particles settle out. A more sophisticated but common laboratory method to assess soil texture uses a hydrometer to measure the specific gravity of an aqueous soil suspension while settling. The measurements at successive time intervals show the proportions of sand, silt, and clay. Soils that have a high clay content are often referred to as heavy or fine textured, whereas those with a high sand content are called light or coarse textured. The terms heavy and light refer to the apparent ease at which the soil can be plowed. Rarely are soils made up of a single type of particle. They exist as combinations of sand, silt, and clay. So scientists have developed 12 basic classes that describe the texture of typical soils. The USDA Soil Texture Triangle is a generally accepted scheme for classifying soils with respect to the relative concentrations of sand, silt, and clay. These classifications are extremely useful. The chart is read by knowing the percent of sand, silt, and clay in a soil, then following each percentage line across until all intersect. Now let's consider a specific situation. What would we call a soil that is 20% clay, 40% silt, and 40% sand? We would look at the USDA Soil Texture Triangle and read off each component. Sand, silt, clay, and the answer would be loam. Loam soils are considered optimal for most crops. The common names of specific soils typically combine the soil texture and the name of an individual or the area in which the soil can be found. For example, Crosby silt loam soils are found in Columbus, Ohio, and Worcester silt loam soils are found in Worcester, Ohio. If the soil contains significant amounts of gravel, the soil name will often include the modifiers gravelly or stony. Miamian is a loamy soil type that is the most commonly found soil in Ohio, occurring on more than 750,000 acres. The Miamian series consists of very deep, well-drained soils that formed in a thin layer of less and in the underlying loamy till, which is high in content of lime. The original vegetation consisted of deciduous forest species, principally white oak, maple, elm, ash, and hickory. Miamian soils are productive soils. Corn, soybeans, and winter wheat are the primary crops. Now to summarize, soil texture is an important soil characteristic that drives many uses of soils, such as crop production and field management. Texture is determined by the percentage of sand, silt, and clay. Texture influences drainage, water holding capacity, aeration, susceptibility to erosion, organic matter content, cation exchange capacity, pH buffering capacity, and soil tilth. We will elaborate on many of these parameters in other units.